Okay, this is going to be quick. Yeah, got Tinshu from Pure Storage, Roger from IBM, Shyam from Marvell, Craig from Marvell, and Nishant from Marvell. So it'll be cozy. Hopefully, maybe somebody will wander in here and we'll get going. So I'm going to do an update on where the standard is with regard to fabric notifications. So we're going to just walk through, where we started with the problem, what the solution is, give you some examples. We're going to do a demo of the fabric notifications functionality in action. And then finally, I'll wrap up with an update as to where things are implementation-wise, so that those of you that want to take advantage of it can basically go out and buy it, install it, run it, and make it work. The problem is pretty simple. Of course, then I hit the wrong button. Okay. Problem is pretty simple. What we've been dealing with, and this is not unusual to any of the transports. So every transport has this kind of an issue, which is quite simply, you're going to have persistent intermittent errors in your fabric, in your deployment. So we're talking pretty much storage when we talk about fabrics, so storage fabrics. And those persistent intermittent issues are associated with either some transient type of issue on the physical side or some intermittent congestion problem on the logical side. The reason it's persistent is because it seems to happen pretty much every time some I/O or job starts up, some weird issue and performance drops either here or it drops over there. You can't figure out quite what it is. It's intermittent because you can't exactly figure out exactly where and when it's going to happen, but it does happen. So what we find is that when we talk to customers, they will say, yeah, I've got this job, it runs, some days it runs fine, other days performance drops off, and figure out what's happening. So the key thing that we're trying to solve is what is going on. One thing about multipath solutions, which a lot of fabrics do, so we're going to define multiple paths between the servers and the storage. That way we have redundancy and can get at it, or we can balance loads across those multiple paths. One of the things that we found out is that when these persistent intermittent problems start to occur, the multipath solutions cannot figure out whether it's logical or physical, because of the tools that they have available to them are really at a much higher level. That is, the only way they know something's going on is if they're sending I/O. If they're not sending I/O, you're not going to generate the problem, and you're not going to have an issue, but you're also not getting any work done. You start sending I/O, problems start to occur, we can't figure out, is it logical or physical? MPIO layers, often what they do to deal with this particular problem is they implement what's called a health check. I have a problem on this path. So that path gets set up as marginal. 2-3 minutes later, I'm going to take my marginal path, make him active again, and try I/O on it. So you end up seeing this kind of sawtooth behavior of these health check cycles that occur. And again, that's because the MPIO solution does not have a direct way of understanding when there's a problem in the fabric. The causes of these issues are they're common to any transport. Cables, SFPs, all the connecting points. Those are the link integrity issues that tend to cause problems. They can be, when they're hard failures, that's really easy to find, right? Path went down. All of the solutions available today handle path down, no problem. You get failovers, it's automatic. It's when the path doesn't really go down that things really get to be a problem. What we have discovered in the process of evaluating this particular problem is that the way I/O works is that oftentimes we're doing a read modified write. So we get out and we do the read. If that fails, we're hanging around because we need that read data in order to do the next step. So what you'll see is performance will go down to near zero when these issues start to occur. Well, you would think, well, why not just use the other path? Well, there are timeouts that are involved, especially at higher up the stack levels. So at certain points in time, you can have a particular command waiting maybe 30 seconds, 60 seconds, depending upon the configuration of the environment, for a response that says, hey, that command didn't make it. And then I can retry it, and I'll retry it on an alternate path because I had an error. So I had a timeout on that path, so I try the other path. Or if I'm able to determine that there is some type of an error, which is, again, very seldom because of the nature of the way the path selection works, I can try it on another path. But I'm not going to try it until I'm sure that that particular I/O has failed completely. And that takes time. So we end up with these big, near zero performance levels with something that is supposed to have redundancy, multipath, to alleviate that particular problem. So one of the other issues that comes into play is congestion. And a lot of congestion has to do with the differences in the device capabilities or differences in devices' behaviors. So Nishant talked about this a little bit earlier, but if you have an environment where everything is pristine or everything's all at, say, Gen 7 fiber channel, for example, everything's working fairly well, and all the traditional mechanisms give you feedback to allow the adjustment for the changes in behavior, based upon I/O demand and I/O response. When you have an environment where it grows organically, some of the pieces are Gen 7, some of the pieces are Gen 8, some of the pieces are Gen 9, some of the pieces are Gen 4, some of them are Gen 3, somebody's cobbled these things together, and you got this great disparity between the capabilities of the switches, are the devices, not just the switches, but just the devices. And one device may say, hey, I'm going to do a large I/O, say a server-based backup, and he goes out and grabs it all, but he's, say, a 4 gig device. So he's trying to pull back and consume data at a 4 gig data rate when the rest of the infrastructure is sending it around at 32 gig or 64 gig. One of the reasons that we've seen this more and more occurring more and more lately is just because of that disparity in generations of products. We've got a lot of technology out there that everybody is trying to leverage. And as they try to leverage it, be cost effective about it, that's when you start to see some of the issues. The other thing that we're seeing is that the tools, the switches, the HBAs, the storage devices, they've all gotten a lot better about detecting issues. The thing that we haven't really gotten good about is telling each other that we've detected issues. And that's where fabric notifications comes in. The concept is very straightforward. There's a small piece of information that me as the switch, or you as the storage, or the server, HBA, can see. And all we want to do is be able to provide a mechanism for these individual components to tell the others, hey, I see an error. When the MPIO layer is able to tell that there is a problem in the fabric that is due to a physical issue, he can make a much more intelligent decision about whether or not to use a particular path. So for example, if you have a link between the storage device and the switch that is intermittently getting errors, there are tools in the fabric that will say, hey, if I get more than 2 CRCs in a minute, that's a marginal link. So I'm just going to surface a message that says, I have a marginal link here. When that message gets up to the MPIO driver, he can say, that's a marginal link. So, and I've been told explicitly by the switch that that's a marginal link, or I've been told explicitly by the storage device that's a marginal link. I'm not going to use the marginal link. I'm in my path selector, I hang that on the wall and say, he's marginal. I shift all my workload to the other path, and my performance returns to 100%. Fairly straightforward. The fabric notifications functionality is broken into 2 pieces. We have a mechanism that is essentially software-based, which is we'll call it a signaling mechanism that the devices can tell each other, hey, I found this. Then we have a physical mechanism that is designed specifically for a credit stalled condition, where you're not able to send a software-based message because there's so much congestion at a point that you can't drill through it. The hardware-based signal can get inside the link and actually drill through there and get the attention of the other device to say, hey, my resources for you are all being consumed. You need to do something about it. In the case of a link integrity issue, the mechanism says, we found a problem. We had more than 2 CRCs in a minute, so We're generating the issue. We signal the fpin link integrity notification to the server, and the server, via the HBA and up through the operating system stack and into the MPIO layer, makes a change. For congestion or peer congestion, so congestion is occurring at a particular port. And what we want to be able to do is tell the devices that are accessing that port or have access to that port, hey, there's congestion here. We also want to tell that device, you are congested. So the first thing that we'll do is we can send a congestion notification to the congesting device to say, gosh, things are congested here, can you do something about it? Simultaneously, we can send another notification to its peers to say, you know what, if you're going to send I/O to this device, please note it's congested. Now, this is just information that can be provided to the end devices, and the end devices can decide exactly how they want to address that particular issue. So an end device may want to cover this at the HBA level and let the HBA just manage it, or they may want to push that information up the stack and have something like the MPIO driver on the server side deal with it. So there's options there with how we can manage it, but the fundamental mechanism is key. We have this messaging, a small little bit of additional information to be able to identify these issues. And then finally, is the case of the delivery notification, which is more or less a special case that can be associated with the transport protocol. So if we take SCSI, for example, if we know that somewhere in the fabric that we have discarded, for whatever reason, a valid, clean SCSI command, we can send a notification back that says, this command is not going to get to the destination. And then the source now has the ability to be able to say, oh, I can either retry that, or I can just simply say, that I/O has failed, and then let the upper layer take care of it. The intent of that particular notification is to reduce that upper level timeout that is going to be more like a 30-second timeout to something into single-digit seconds. So the intent there is really to get a response or an action much more quickly than we have in the past. Once that condition is detected, we say, hey, source, we dropped the frame. And it was a command frame, and you might want to know about it. Again, it's up to the end device implementation or the layers in the stack to decide exactly how they want to deal with it. So they may have other mechanisms for managing error detection and so forth. They may want to merge that. But this is just, again, just a little piece of information, additional information that it didn't have before. So more intelligence can be built into it to be able to make a better decision about what to do. The congestion signals are designed, as I mentioned a little bit earlier, to deal with credit stall. And that's in a lossless environment. That's the case where I've said, I've got 10 credits to be able to receive frames, and I've used them all. So I can't send you credit back to say I have any more place to put frames. When that particular condition occurs, what we see is that I/O starts to build up at the transmitter. So in my example here, I'm just showing that I/O to the host is building up at the switch level. When it reaches a particular threshold, we can then send a signal, hardware-based signal that says, you're over threshold. And then that signal can occur at a particular rate that is negotiated based upon the participating devices. This is a very effective way for the two pieces to basically find the red line, if you will, of the performance metric for them, for being able to receive or for the transmitter to be able to send data to the end device. So let's go through a quick demo. In this demo, we've got an AB fabric set up. This particular demo is going to show EMC power path taking the actions in this particular case. It's going to be a Linux environment. Like I said, it's AB, and we'll first walk through how the mechanism works without fabric notification, and then, which is traditional, and then how it works with fabric notifications. One of the things that I want you to look for as we go through the demo, and I just have two examples of implementations that are already out there. In Linux, in this example, you can see the blue line there shows what would normally be a baseline. You know, that's I/O, no errors, both paths available. The green line shows what happens when you have fabric notifications and you get a link integrity problem. What you'll see in that drop there is that first instance that says, oh, I had a frame that got hit. I'm waiting for it to time out, trying to figure out what to do next. Meanwhile, I get a notification that says you have a physical error that occurred on this particular link. Once the MPIO solution figures that out, it says, okay, I'm not going to use that path anymore, and performance comes back to almost near capacity in the AB fabric. The red line is just showing what happens if you don't do anything with it. And you can see that performance drops off pretty considerably. And there are periods of time where you have performance at near zero. AIX is just another example. We actually kind of drilled into this one a little more closely, and this is just, the green line is just representing the kind of the nature of the test, and that is we're just shooting I/O out there kind of at a particular rate, and just that's kind of an anomaly of the tool. But the basic pattern is still the same. You're going to see a drop, a detection that it's an issue, and then performance get restored to almost 100%. The reason I wanted to point out both Linux and AIX is just to show that different OS implementations are able to achieve very, very similar results with just a basic modification that we've already been talking about. Okay. Okay, come on. I know. Let's try this. All I did was switch applications. I'm hoping that this will, there we go. All right, now we're in. Okay, I got what I need. All right, so as we go through this demo, first thing it's going to do is just show you that it's an AB fabric. And it's just, just showing you that there are two different ports on the symmetrics, a couple of ports on the server. They go through an A switch and a B switch. So it's just giving you that particular view so you know, okay, I've got my AB fabric set up. The next thing it's going to go through and show you is just some statistics about the two paths. And then he starts I/O. So pretty soon here we're going to see I/O pick up. Now you can start to see it pick up. And then we start injecting errors into the I/O. So at first, everything's running along fine. Then error injection is going to occur here shortly. We can see here both paths are being used. Now the error occurs. And this is where, this is common. In every multipath solution that we've tested, this exact same behavior occurs when you have a link integrity problem. And this is where you get to the near zero behavior because he's waiting for that to completely time out before he can start the next request. And then you end up with this kind of sawtooth behavior of performance degradation that's occurring. So in the next portion of or in this, what he's just showing you here is that, yeah, we go to zero on one path, and then we end up doing the same on the other path. So now he's just going to stop and show us that, look, these are the CRC errors that we were seeing as we did this. So we know that the fabric's detecting the CRC errors. We see the sawtooth behavior on both paths. And that's, I want to stop that for just 1 second. That's critical because now you have just one link in the system that's causing problems, not for the path that's being used, but also for other paths. And that's one of the things that we found contributed to that whole drop to near zero performance characteristic. Next thing he's going to do is we're going to go through here and we're just going to set up the two fabrics so that they enable fabric notifications on both of the switches. As he enables the fabric notifications on each one of the switches, activates that and says, okay, we're ready. Then we're going to go out and we're going to verify that it's been activated. So I'm a little bit ahead of the demo here. He's still just working on enabling the FPIN event on fabric B And now he's going to show us that when we look at it, we can see that the devices have registered to receive FPIN notifications. And then we'll look at Fabric A, and the devices there have also registered to receive the notifications. So now we're armed. We have a mechanism now to be able to handle this. So we start things up, get I/O flowing, and then inject errors. So here we're just making sure that we have I/O going on both paths. So this is just off and running. See, we're looking at both paths, and they're both going. Inject the errors, and just as before, we see the drop off. So initially, you're going to the MPIO layer still has that problem. Hey, I'm waiting on the recovery. I can't tell if that I/O is complete or not until it times out. But it's the next step that's key. Since he's waiting on that, he gets the notification that says, the reason you're waiting on it is because of a physical error. So don't use that path. So he quits using that path, but continues using the good path. And then when we go back to it, what we'll see here is that the performance levels, what he's showing you here is that, hey, I sent an FPIN, and then what you see is that the performance levels come back up to near 100%. Because now he knows for a fact, I'm not going to use that path that has the intermittent errors on it. The other thing that we found is that latency also ramps up when you end up with a system that's trying to process the fact that he's got errors. But when you take those persistent intermittent errors out of the equation, latency may go up initially, but then it starts to fall off because he knows, oh, I'm not dealing with those errors anymore. So effectively what we've done is isolated the bad path and said, hey, you can deal with that later. Along with the notifications, the systems also have mechanisms for alerting the administrator, hey, we have an error over here, and then they can deal with it, not as a critical situation because their application went down to 0, but more as a maintenance function where they said, hey, application's running fine, everybody got through it, but oh, by the way, we lost a redundant path. So let's schedule maintenance on that redundant path. So the value there for the customer is that we've gone from a situation that would normally cause a critical escalation to a situation that's just a standard operating maintenance function for the administrator. Okay. Back to the regularly scheduled programming. All right, we got it. So just as a review, these are the benefits of Fabric notifications. We effectively are able to maintain the performance with a multipath solution because the multipath solution is able to identify explicitly that he has a particular path that has a physical problem. And that's something that it could not do before. And lest we think that this particular problem is unique to SCSI, we tested NVMe. Guess what? NVMe has the same issue. In our preliminary testing of iSCSI, guess what? iSCSI has the same issue. And the problem is fundamental. The problem is that the upper layer that's trying to make the decisions about what path to use is missing a little bit of information. And that's where Fiber Channel Fabric notifications came into play. Just by adding that little bit of information back to the equation, those tools can do the thing that they're supposed to do, which is to maintain high availability in the environment. So some of the use cases. So how are we going to use these things? Let's start with just problem determination. Classic case. I'm a storage administrator. This persistent intermittent problem comes into play. What's the first thing that happens? Application owner says, I'm getting crappy performance. Calls up the SAN administrator, says, I'm getting crappy performance, I'm going to this storage. He calls up the storage administrator. Your storage sucks. Storage administrator says, I don't see anything in my logs that says my storage sucks. So they do an analysis. So they go through and they call in their support guys. And the support guys look through all the logs. The support guys look at all the performance characteristics. And they say, you know, everything looks good to us. Ask the SAN guys. Next call. The Fabric administrator. Fabric seems to be having a problem. Some point in time, the fabric finally goes, oh, yeah, I think we see an error that's occurring over here. They finally put the two pieces together, and 2-3 days later, you go, aha, we know why your application is running poorly. We found a bad cable. We fixed the bad cable, and so you should be good. Problem is that storage administrator was involved, level 3 storage support was involved, SAN administrators involved, probably level 1 or level 2 SAN administration figured it out. Application guy has to suffer through days of bad performance, and it's all because we had a bad cable. That's not a good way to run our environments. By adding back just this little bit of information, by just having the devices register to receive fabric notifications, and the only thing they do is log it, they can cut down problem isolation determination to minutes. That call that says, hey, Mr. Storage, your storage is bad. He pulls up his log and goes, my storage is not bad. That host is oversubscribed, or the path from that host has a link integrity problem. So you go from involving 20 people in an analysis of the situation to involving one person who pulls up and looks at the log and says, nope, that's it. Information in that log data also tells him where in the system that link is bad. So rather than digging around and going, well, is it this link or this link or this link? He goes, no, there's that link right there. Clean it, you're done. From a storage administrator's perspective, that's a beautiful thing, because I have saved all sorts of time for my team having to go through and analyze this thing only to find out that it was a dirty cable. And now I have a very quick way of being able to say, it's not me. Check the cable. And not only that, I can also say with confidence, check that cable, not that one or that one, but that cable. Because that information is also in the notification. So for problem isolation and determination, being able to, having the devices enabled with fabric notifications gives you a huge step up in being able to support your customers. Link integrity isolation, I think we've already gone through, because that's been my example throughout the presentation. So I'm going to skip it. Target credit stall. This is a really difficult issue. This is when the resources inside the target get so consumed that they're not able to push things up to the CPU anymore. So that can be, there's a number of reasons that this can occur on. But one of the common reasons is the target's oversubscribed, and he's trying to push a bunch of commands that need CPU processing up. That queue gets full, it backs up into the HBA, and then the HBA backs it up into the fabric. In order to be able to deal with target credit stall, the signaling mechanism will tell us this is an issue. If the target knows, oh, I'm backing things up into the fabric, then it can do an evaluation. Hey, I need to take some sort of an action and deal with it. So it can look and say, oh, is my queue up to the CPU full? Oh, there's my problem. I can't process things efficiently. I mean, I've been sending stuff up there and the CPU's not being able to process it. I need to do something with it. One of the things it could do, it could just flush that queue and say, you know, those transmissions are done, because there's no way for me to get to them in a timely manner because the CPU is busy. That's an option. But the only way that mechanism works is it knows for sure that things have backed up to this point and are a particular problem. The other thing that can be done is that the target can determine if it has a frame discard timeout that could possibly occur. If that is occurring, then it can say, you know what, I'm never going to be able to process the particular frame in a timely manner, and I can just drop it or discard it, allowing more room for frames that I can process to come on in. So there are various mechanisms that can be done that are based upon the fabric notifications model for the target to deal with target credit stall. The other thing it can do is the target can send a fabric notifications event to the servers and say, look, my resources are being filled. I need you guys to back off. So if he's oversubscribed, which typically occurs by organic growth of the zone information, that is, new servers as they were added, knowing they have to get at a particular volume, are just simply added to the zone. When you get up to 16 to 1, all of a sudden that, and they all say, hey, I want to go see, I want to go talk to the target, they're oversubscribed almost instantly. And then target credit stall comes into play because these 16 servers are jamming the target with commands that they want, little bits of information out of the target about. So the target can now say with fabric notifications, please don't send me any more frames because my resources are being consumed. So now there's a back-off mechanism that is built into the system that can leverage just this notification mechanism. Read over subscription can be managed at the HBA. It's very simple. HBA just says, hey, I need to slow down the rate of read requests in order to give my server a little bit more time to process things and not back things up into the fabric. One of the things that we found in testing is that it doesn't take that much. You can have an HBA doing reads, just trying to peg the fabric, and the other devices are suffering because there's some common resource that they're contending with. So you have essentially a bully flow, say doing a server-based backup, for example, and then the other guys, their production stuff can't work. The server-based backup guy is told, hey, you're consuming too much, back off a little. All he has to do is back off a couple of percentage points in demand of bandwidth on that particular path, and the other guys get in. And all of a sudden the fabric is able to function more effectively, and you don't have victims who say, hey, what's going on? All of a sudden my performance went to 0. And a SAN administrator going, well, I don't know what happened. Let me see who came on. Oh, 24, 48 hours later, they figure out, oh, this backup's hit. And that's why we saw congestion here. And then that's why we saw it. Instead, the server automatically takes an action just to back off a little bit. Like instead of trying to push it at 110%, we push it at 95%. The other applications now have breathing room. They continue to perform at a reasonable level so that the user's not unhappy. So maybe they're performing at 85%, but it's good enough. And just a tiny action by the server from an instantaneous notification from the fabric did the trick. Write over subscription is the same thing, only in reverse. So I won't spend too much time on that, except that it's the target who will be doing the backing off. Same issues that we have with link integrity can be managed in array-to-array replication so that when you have multiple paths for the storage device, and they know that one of those particular paths is not good, via the fabric notification, now the target can say, you know what, I'm not going to use that path because I got plenty of other paths. So the array-to-array migration kind of stuff can happen much more efficiently in the face of errors. So where are we? As far as the standards are concerned, we began this effort in 2018, late 2018. The fiber channel standards worked through all of this stuff. Everything's been fully specified as of April of this year. The specifications address framing and signaling, link services, and switch fabric operation. In September of 2020, we actually had the first introduction of devices that support the fabric notifications capability. Both Brocade and Cisco, from a fabric perspective, support it. You can see here with the initial releases of it. Both Emulex and Marvell debuted in September of 2020, as well as supporting the functionality. So it's alive and well today. MPIO solutions, which is the next layer up that we really needed. IBM AIX was the first to bring it out, followed very shortly by Red Hat Linux. They brought it out in November of 2020. In January of 2020, PowerPath, or 2022 this year, the PowerPath solution that I just showed you in the demo became available. As of May and June of this year, we've done an inbox version on the Red Hat. So the very first version of Red Hat required the EPEL package. So that's a little bit, from a distribution perspective, that's difficult because customers have to download the EPEL package and activate it and so forth. That's a little bit harder to get customer penetration. We inboxed it and also released it with SLES this summer. So those are two big steps for the Linux side. On the storage side, Pure supports this, as does NetApp. So as you can see, we've got some momentum in the Fiber Channel community with regard to support for fabric notifications. And certainly my hope is that this mechanism becomes much more prevalent. For me, that's a wrap. I do want to thank the FCIA for giving me the opportunity to speak here at SNIA. This has been a cooperative effort amongst all of the ecosystem partners within Fiber Channel to bring this to fruition. In summary, first of all, thanks for attending SNIA, the Software Developers Conference. It's a great opportunity for us geeks to really geek out. So thank you for joining. We've gone over the problem and solution. Problem is common. It's, for all fabrics. The solution is just adding a little bit of information from the participating components. We've gone through functionality and use cases. And as you can see, the deployments are available today. So the message forward is customers should demand that they want true multipathing capabilities. And that's where fabric notifications comes in. You want to employ these devices throughout their fabrics. Once we have these more intelligent mechanisms, true SAN, automated SAN mechanisms can really come into play. And then lastly, please deploy fabric notifications both in your solutions and in your environment. Questions? All righty, yeah.
When you did your NVMe experiment,
Mm-hmm.
did you notice a lesser drop to zero because of the rack or flush support in that protocol?
It was different. Go back to that chart. It was very different because of I think it's more because of the multi-queuing here. What we saw were smaller gaps at zero, but also smaller gaps at full throughput. So it was, let's just say it was more erratic, but the overall was the same. I mean, your performance is going to drop to near zero because you literally spend time at zero I/O while you're waiting for the response.
Single-threaded I/O, you had multiple threads.
And we've done testing with multi-threading, and then what you see on the paths with multi-threading is that it appears in a multi-threaded solution that there's more I/O going over the path. But the other thing that you see is that you still have these applications that stop while they're waiting on, because one of the applications that's being serviced by one of the threads gets hit. Exactly. It's harder to see. From a port level, it looks like, oh, this port looks pretty good. But then when you start breaking it down by application, you go, okay, this application is really not doing well, or that application is not doing well. And then the bigger problem with what we found when we were doing the testing was it was harder to identify who was being hurt and who was causing the problem, or if it was a congestion issue, but who was being hurt by link integrity problems was a little bit harder. Like you run the test once and application A would be the one that got hurt. You run it again and application C is the one that got hurt. And it's because of randomness of whose I/O is going to get hit by the link integrity problem. Yeah.
Yeah, know what the hyperscalers have been doing? I'm hard to believe that they were running around cell phone yelling at each other.
I don't. I really don't. Yeah.
I understand that, but which to me sounds scary. NTSC with only add-on eventually cost because any other.
Yeah, I haven't done a lot of work with the hyperscaler environments to be able to say, it's susceptible to the same thing. We have done Ethernet work with iSCSI, and we see exactly the same problem. Our next set of tests, we're going to do NVMe over TCP, and of course just some TCP storage or IP storage using TCP. Those will be our next two tests, but I suspect those will behave the same way, because the multipath solutions above them are still very, very similar in their behaviors. No, we're just going to do the error profiling. Yeah.
You're good engine,
Right.
What happens when you break?
Exactly.
create the problem before we solve it.
Right, right. I mean, you know how it is trying to get things like this through the industry. I mean, you saw my history slide. We started in 2018, and 4 years later is what it took us to get enough of the ecosystem deployed so that you had an end-to-end solution.
The solution requires a software upgrade of the HBA or a hardware upgrade of the HBA?
Depends on the generation of HBA. So the way the vendors are rolling out the solution is that the solutions work with Gen 6 and Gen 7 fiber channel. And then, certainly on a server side, you have to have an OS that supports it. So we're talking Red Hat 8.3 or higher, SLES 15 Service Pack 4 or higher, or there's not much higher.
So today, any HBA vendor supports full functionality of that thing, including link integrity and all that?
They both do.
If you're writing your own drivers, there's no hardware dependency whatsoever. You just link services. And it's not hard to change it, register, at least for monitoring.
I guess there are two aspects to the.
Now, see how disruptive this could be for the customer. That's what I'm trying to figure out.
Right. So,
You have a multipath, you have two adapters anyway, so you can.
right. And normally what happens, the way customers deal with it, they never deal with it at the HBA level, right? It's a server. So when the server's seen its life, out goes the server, in comes the new server. And the point there is, as long as the new server has Gen 6 or better HBAs in it, you're golden. Yeah.
So next time it's German,
Right.
everybody will have it automatically.
Yeah. And the fabrics are the same way. The switch customers, they're not going to just randomly go out and pull out a switch. They're going to wait till the cycle for that product is done, and then when they move in the next cycle, okay, hey, this is a reason for me to choose, Gen 6 or Gen 7 over a Gen 5.
Would this chart look different if you had random flush implemented?
Oh, you mean sequence level error recovery implemented?
I would think so, but
It probably does look a little bit different. Test number 3. I mean, that's scenario number 3 that we're at too. I mean, I've got.
It still takes 2 seconds to detect a lost train, don't
Yeah. Yeah. It's a bit longer. These are roughly 20 to 15 seconds, depending on. But that's the nature of the beast. You're out, something happens, you don't know. In the upper layer, has no idea. Was it physical? Was it logical? We've got, the architectures have timeouts, so they've got to wait for that timeout in order to make that determination. And the whole goal of fabric notifications was to take this little delay right here and provide something that said, sooner, that said, hey, it's not logical, it's physical.
But they're not reacting immediately to the event, other than, after the timeout occurs, you go look for an event, they always stop using the path, and then
That's the way the implementations are today, as far as you could.
see the event and go, hey, I'm not going to wait for that IO to complete it.
You could do that. You could do that.
But you kind of have to, you got to flush it out or something.
Right, exactly. You either flush what you sent out, or you wait so that you know it's clear.
traditionally, so in our solution, if the HPA detects the drop frame today, when if the frame was dropped at the endpoint where it came into the adapter port, we would do a retry immediately because we know that it happened. But any drop on the fabric or the storage today is not notified, and we cannot take that action.
Right.
And I think FPIN enables that.
Exactly. FPIN can tell you it was dropped.
Notify the host of the drop, right?
That is correct, but
It's still at the timeout.
Well, the switch, if the frame is dropped in the switch, that's up. Where did I put that? Oops, no, I'm going the wrong direction. The frame's dropped in the switch, he can tell you.
But you need the storage participation to send a notify if it's.
Yeah. So if the frame's dropped here, and it was a command frame sent, from a host, or even a command frame from a target, if the target's acting in initiator mode, you can send the notification and say, that command is, I know I dropped it, so it's up to you to deal with it.
If the storage dropped it,
Yes. You're right, right. If the storage says, he gets it down here and says, you know what, my resources are consumed, I'm going to send a notification to the host to say back off, and he drops it, then yeah, he could send the notification.
Aerospace, they extra heavy PCI Express has advanced error reporting. Could live with that. Your customers will, or was your solution so reliable that it was so rare to have this problem?
No, yeah, it's a great question. What the hell took us so long? I have no idea.
The GSM standard had something like this, where you switch from one base station to the other one in case the media.
Right. I agreed. No, I totally agreed. Why did it take us so long? I mean, part of my answer there was we needed a certain level of maturity in all of the components to get there. But yeah, no shit.
Like he said at the beginning, all of this stuff was detected and recorded in some way before, but it wasn't coordinated. Right?
Yeah.
It wasn't, the sharing wasn't happening.
Right.
And that's why it was
Yeah.
A supervisory role where
Yeah. So yeah.
a lot of finger pointing.
Exactly.
Different vendors implement different parts of it.
Rather than working as a community.
your solution works with this solution.
Yeah. Yeah.
Okay, good.
Guaranteed. Guaranteed.
Okay, good.
Yeah. Yeah. That,
And dialect. All right.
yeah. Yeah. Exactly. Yeah. To give you even further background, we had kind of an aha moment in November of 2014 that said, if we could do something, then this customer would be screaming at us so loud. And it was at that aha moment that brought us down the path. So if you add that into the, how long's it been? We're 8 years. 8 years to get to this point. Yeah. I mean, it's an unfortunate side effect of our business, right? You're in the storage business. Stuff lives a long time.
Well, but the sheer amount of dollars going into, let's call it flash,
Mm-hmm.
then there's a chance to get disrupted. That was my question. What do the Google and the Facebooks do? They probably ignored you guys and came up with their own solution.
Yeah.
And just check, Google put something similar on this open source.
Right. So there are various forms of like out-of-band DevOps kind of things that people have cobbled together. I mean, we had customers, everybody's kind of doing it a different way. We had actually one customer who had kind of a quasi-human system for link integrity problems. The way it worked was that when a link integrity problem occurred, they automatically fenced the port, and then it would generate a service ticket, and then that would get put on a person's queue, and then that person's job was to take the service ticket, find that port, toggle it, clear the error, put it back on. That's how they did it. Guys, I'm out of time. I certainly and sincerely appreciate your time here today. Thank you all very much.